everybody. My topic's name is Development of Storage and Analysis Methods of Multidimensional and Heterogeneous Data in Parallel Systems, focused on the use of analytical streaming tools. So the main aim is development of new methods for organizing memory with parallel access to a wide class segments contained with multidimensional arrays. And there is a picture of memory models which connected parallelly. Here you can see different types of bus and how they connected with each other. So this is for data bus, RW is for read-write bus, and alpha is address bus. How we connect to every memory model. So there are a lot of methods of accessing to data, and one of them is tree-like data structures. Access to tree-like data structures. So in general, parallel memory is designed for obtaining conflict-free access to arrangements of cells that belong to a specified set of data templates. Trees is also important data structure, and parallel access to a subtree means the conflict-free access to all nodes of the subtrees. There are several known results and known theorems, and I will present 3 of them. First is about a parallel conflict-free access to all nodes of an arbitrary complete Q-array subtree of height T of a Q-array tree with a special recursively linear model assignment function. So, and everything is possible if the number of memory models is equal to Q in power of T minus 2. So you can see the formula on the screen, yes. And the second theory is, so every theorem is about tree-like data and their access. And so the second theorem is about the minimal number of data models. So you can see the theorem here. Again, I can read. So, and the third theorem is about also conflict-free access to layers of subtree, to all layers of subtree, and how it's possible with so how it is possible to have a parallel conflict-free access to memory models using a minimal number, which is calculated by those for that formula. And at the end, I'd like to say about types of subtrees, which was all those 3 theorems about. So the first one is complete subtree. The second one is complete general extended Q-array subtree. And the third is complete left extended Q-array subtree. Q-array means like here is 1, 2, 3, 4, 5, 6, 8, 9 array subtree and vertices. So that's all.
And what is the task?
The aim?
What's the task?
To develop new methods to accessing data, multidimensional data. So there are several problems that we have, and I have now, like, it's only beginning of the work. Now I am learning and not discovering.
How you consider that you have developed new method? What is the okay, a little modification of some existing method will
will be a new method.
So that,
for example,
why it's
nowadays,
master work?
For example, nowadays all work was made only for one-dimensional. Our stuff is making it multidimensional, and it's a big problem.
And what is the problem?
Problem to accessing to multidimensional data, not one-dimensional data, parallelly. That is the problem.
Why it's a problem?
Because there is no solution now. No solution like a mathematical model solution.
Yeah, okay. So you have some problem that's you have no method.
Yes,
acting with multi-dimensional.
Yes.
Yeah?
Yes.
And you already discovered that there are no methods. Probably.
Yes. So now we're working on it. And now I'm learning some new articles and old articles.
Yeah, and what kind of tasks you should perform to approach to your target? What you need to develop. But methods is one and big task for probably big task for the whole your master thesis, but can you decompose it into tasks?
Now I have one task is I showed here 3 theorems, and it's a known theorems, and all of them was made for one-dimensional data, and now I need to make it for multidimensional, and this is a little task for me now. My task for 2 months, for the next 2 months.
Little task to prove these theorems to multidimensional data?
Yes, like he said to me to do it in 2 months. That's why I'm working on it now.
Okay.
That's all.
Other questions?
Why?
For fast access to data.
What kind of systems use this approach?
I don't know now. Truth be told.
Okay.
That's all.
Yeah, actually you need to provide this information in master thesis.
Of course,
Because,
but it's the beginning of the work, and we
Yeah.
have started just.
Why do you need to solve this problem? Work around.
Okay.
Yeah.
Okay. I will read and ask about it of my scientific advisor.
Okay.
Thanks.
Okay, thank you.
Hello everybody, my name is Andrew Marinov and my scientific advisor is Alexander. My topic of research is brain activity analysis using methods of machine learning. That's a very wide formulation, but that is what it is. So first of all, I want to remind you some notions of brain activity analysis. Which sensors do we use to obtain the data? First of all, that's EEG, electroencephalography. The method that is already more than a century, has more than a century, has a history. As you can see, its main concept is reading the data from electric stimulus running through the skin of the head of the test subject. So it allows us to get some information, but it's not quite clear what that is. It's very noisy data, usually. Doesn't correlate directly to the brain activities. A lot of analysis needed here, usually. Now, more new methods is functional MRI, magnetic resonance imaging. That's a technology that's based on the principles of finding where the blood in the brain is more actively pumped in because of the activities of the brain. That is based on the principle of magnetic resonance, because blood has magnetic properties, and so that's why we can make this possible. It's a very precise technology. It allows us to get to a resolution of about 1 millimeter. But that's a very new technology, by the way. I think it's about 20 years or 30 history. Analyzing the data that comes from this is a very hard task because, first of all, brain is not very sustainable, not easily understandable system. Sometimes we have random thoughts. Sometimes we have some unconsciousness driving activities in our brain are different. So they perform the tasks that they are given in a different ways. Sometimes they may develop a new method of performing the task midway the testing or something like that. So to really make some insights into how brain works, a lot of statistics. We should gather a lot of information and analyze it somehow. Unfortunately, in approach to this problem so far is to use p-values. What's this? That's basically a statistical theory proving approach. We gather some data. We have two theories about how this data should be distributed. And by proving that this data has little chances of being gathered, one of the theories is wrong and one is correct. So we collect these statistics. Usually it's voxel-wise. That's it. For each voxel, we collect the statistics. We summarize it. We get the test statistic that is normally distributed, standard normal distribution. And then we get the p-value. How probable it is for us to get this data. And if this probability is very low, then we consider, in this voxel, we have some interesting activities. So that's considered an active part of the brain, and it is highlighted by red, yellow, or other colors on the brain map. So here, T should be fixed a priori, and that's that's a thing that some researchers may vary as they want, as they please, to get some very specific results or more general, or well, it is unknown how to get the best threshold value. And this approach has other problems. For example, we need a lot of statistics to get good p-values. For example, we lose a lot of information by averaging, because, I mean, if we have thousands of samples and we just collect it into one value, that's losing a lot of information. You may, it's obvious, I think. Possible solution for this and some other problems are reproducibility analysis. Now, in general, reproducibility is a measure of how close the data is within one experiment conditions. So we need one subject, the same tasks, well, maybe not the same, but similar, because brain can adapt to the task and remember them. But we need to meet the conditions very precisely and calculate how close the achieved data is to among itself. Here's a little plot illustrating this. With the red lines, it is depicted a good reproducibility statistics, and with blue, bad reproducibility statistics. So if these data both provide us with some p-values, some good p-values, quote unquote, to brain voxel. But it's obvious that the left, right? So the precise method I won't get into here, but this method allows us to see more subtle signals, because it's well, to achieve p-values, good p-values, sometimes we need significant from the standard thing. Sometimes we know that in brain some things appear to be calculated just without any effort. So it wouldn't be, it wouldn't produce a lot of blood pressure or something. But we need to know where this happens. So it's important signals if they are reproducible, because if they're reproducible, then that's just how things happen. Also, this method is robust to smaller sample sizes. Well, I cannot prove it right now, but it's just, there are researches that's about this method. So my goals of my research, first of all, is to implement this method on software, because apparently it's not in the standard tools for MRI analysis. And second goal, well, we need to announce the results, some of the possible data sets that we will use include people with depression or preclinical stages of depression. So hopefully, if we make these subtle details visible, we may be able to recognize depression on early stages, and maybe other disorders. Maybe I will adopt this method for EEG data. That's a thing that Sebastianov told me that we would probably do, but I'm not sure about how just yet. And in general, the applications of this method is just better neuroscience researches, because again, subtle details is important. Smaller sample sizes, sometimes it's just inconvenient to collect a lot of data. Things like that. That's all I have for today. today. Any questions?
So you plan to use this technique of p-values?
No. The reproducibility analysis.
Reproducibility.
Yeah.
Can you please go to the next slide? You said the possible applications was is in other disorders detection.
Yeah.
There are many kinds of disorders with the brain.
Yeah, sure.
So how will you classify?
Well,
each disorder? That would be very.
Well, that's a matter of setting the experiment properly. Dr. Sebastianov works at Institute of Physiology.
Physiology.
Yeah. So we have access to real subjects and some data. So it's just faraway goal.
Okay.
Thank you for your attention.
Vipul?
Hello, my name is Vipul Raghuwanshi, and I am a student of second year here. And I am working under Vladimir Barikov of Soviet Institute of Mathematics. And the topic of my thesis is transfer learning with cluster ensembles. So first of all, I would like to define what are cluster ensembles. Cluster ensembling is nothing just using a lot of clustering algorithms simultaneously or one by one. And they can be divided into two parts. One is homogeneous and another is heterogeneous. In homogeneous, let's say we are applying the same algorithm, let's say k-mean clustering algorithm with different values of k. While in heterogeneous, we are using a variety of clustering algorithms. The main aim of this step is just to structure the data in a proper way. Now the main thing comes, the transfer learning. Now transfer learning in machine learning is closely related to a psychological thing that is called transfer of learning. Now this image is actually the best example of this in a common man language. You teach a kid how to walk. You learn this. He learns this model, and then he learns himself to run. If you let loose some wild animal behind him, you don't have to teach him. So something of this phenomena we try to do it in machine learning, and that is what transfer learning is actually. If we try to understand it on from the point of view of data science, it is like, for example, I will take an example first of all of an image recognition system. Now we develop an image recognition system. We develop a lot of neural networks and finally a classifier at the last level. And let's say we are putting the images of cats and dogs in the original image recognition. neural network. But let's say we want to use the same information in radiology diagnosis, that is X-ray. Now, what is actually happening is here is let's say we have thousands of images for cats and dogs, but we have only 100 images of, let's say, X-ray. So we have a very small data set. So making a complex neural network on this radiology diagnosis model is not possible. So what we will do, we will just use the already developed network, which is just classifying cats and dogs. But the good thing is that some minute details like curves, which can be learned in that model, can be transferred to our radiology model. So what is the procedure? Is simple. X is a set of the data set. Y is some object we want to find in that data set. Let's say a cat. But here we want to find some kind of a fracture. So what we do, we just delete the last node, or which we also call a softmax, which is actually classification node, and develop our own classification node for the radiology diagnosis. And we just put two arbitrary weights, W and V, put some random value in them, and then use the information from the previous database and train our new radiology database. The second example can be speech recognition, in which we have a speech recognition system, and we want to train an trigger detection system. Trigger detection is something like you open your phone or you say, "Okay, Google." So it is a trigger word. So, but again, we have, let's say, 10,000 hours of data in speech recognition, but let's say 2 hours of data for trigger word detection. But we can get a very, like, a lot of information from the speech recognition, like how the humans speak, their accents, like this, which we cannot get in trigger word, and can get a much more proper results in our model. Yeah, when it is applicable, when both the tasks A and B have the same input, which means like either it is image recognition, in which the input is images, or speech recognition, which is in which the input is audio. Have the same kind of input. Second point.
transformed to the multidimensional space. In the my slide, we can see the two-dimensional picture, but actually it's 61 dimensional. It's very twisted, manifold of points, but it's not. And we have a measure. And our point put it into some place in this space. So we need to understand which cell is the closest to this one. And to different parameters, for example, like mathematician expectation of the parameters of the cell and standard deflection, derivation of it. So there are many different parameters. And so this is how we can do it. We just compare the different distances. We use the Euclidean method because it can be easily explained in the physics. It's, the Euclidean matrix is can be described by the normal distribution of mistakes in experiments. It also happens in physics. And so we can calculate the different statistic parameters by these formulas. So we have these formulas. We have a function which can describe the probability of all points in the space to be the original point, but with errors. So we can summarize all these parameters and calculate different statistic parameters of it. The most popular and most important to calculate the mathematical expectation of this point. What it's mean what actually this point is. And standard deflection too. Yeah. Next. So the plan. Currently in our lab, we use the brute force algorithm, so we just calculate this function of probability for each point and summarize it point by point. So it's very hard and take a lot of time, about hours for each one analysis, and it's very slow down our experiments. So I try to build a hierarchical data structure which will fasten our checking points. And firstly, I'll try the ball tree, which is widely used, for example, for the space-learn implementation of the nearest neighbor algorithm in this pocket. And I'll try to realize it on C or on C++. After I'll implement it to the laboratory software, which is written in Latvian. So next I'll show you how it looks here construction for points. So it looks like this. We have a common circle which contain all the points of it, and inside it we have smaller structures. So then we will check is this point close to one or not. We can to split to throw out the very big circle of points which are very farther from the current point. I'll show it like this. So I need to define the distances to the each circle for next explanation. So for example, now we can see the circle 2 and circle 4. We can see what the possible distance to the points of circle 2 is lower than lowest possible distance to the points of circle 4. So we can just throw out the circle 4 and don't look at this in our calculations. And approximately calculate the probability of points in this circle like total probability. And actually we can use bypass bars, bypass on width and bypass on depth. Doesn't matter. Sometimes different approach is efficient. Sometimes we will experiment with it. So the results. I've tested the existing library in the ball tree in Scalern. It can give opportunity to find only the nearest neighbor, not to calculate different statistics and probabilities, which I'm going to put in this algorithm. I've calculated the number, how we accelerate the speed of our algorithm. So now I'll show you how work the ball tree algorithm in Scalern. It's just a dichotomy divide. I choose the dimension in which we have the most, the biggest differ between the lowest mean of parameter and the biggest, like in this picture. We have the differ d2 and d1. So d2 is bigger. We choose this dimension and we split it just in the middle. And we built two new circles. That's how it works in real life. So it's not so efficient how I wrote it before, that I did it by hands, but it works, and we still discuss about which algorithm to choose or to split to the hierarchical structure. And this is the already gotten results, which I get by trying this algorithm in the by using the existing algorithm in Scalern as neighbor. So this is the ratio between work of my algorithm and the best work, which was in the brute force algorithm. So different from the model data experiment. This is maybe discussed, but the idea of that one, experimental points, is maybe strongly far from the model points, because lots of mistakes in the data, experimental data. But the speed up is quite big, and then we raise up the size of our database, and as my colleague said me what the size of database equal to 500 or thousands points is enough for too big and quite sufficient mistakes. We have a speed up in which by the number of operations is equal to 50, and this means that my algorithm works 50 times faster than the old one. And the speed, which is, I don't know why it's not so big, it's only 20 number bigger. It's real work in the real machine. Possibly this is because the computer's in-time approximation of algorithms of checking points. Cache of computer and so. And questions?
Yeah, please.
First question, if you've been thinking about implementing the approach Moore was saying about, that L1 measure?
L1 measure, yes. It was forbidden by my scientific instructor because he said what is not physical. So he said me what in the physics we can easily explain only the L2 metric because it's explained how the normal varies of mistake.
Can you list previous 2, maybe 3 slides? Yeah, this one. Did you consider it principal component analysis for this task?
No, actually I haven't read about it yet.
Because it looks like reinventing principal component analysis.
I'll check this
Yeah.
algorithm. I never heard about it. I'll check. I don't have experience.
You will
So
hear
we open for discussion of this. My scientific advisor actually asked somebody who have any suggestions to this, say something to us, and we will try to upgrade our algorithm.
Yeah.
Because
Next
this is
semester
not the best one, and actually the algorithm of which I chose is not so efficient.
next semester you will learn a machine learning course. All this, even principal component analysis and different ones to select dimension.
It's amazing.
And you have some typos on your computation,
Oh, sorry.
compot,
Comparison.
combination,
Comparison.
or
Comparison.
computation,
Number comparison.
comparison,
That's it.
and dimension, and next slide also speed up, speed up.
We also got angels.
Yeah.
Oh, sorry.
Other questions?
My English. We need to be.
Why space number of dimensions is so big?
61.
Yeah.
It's only the measurements on the each angle. So we just measure the results for the each angle, and we have this results. So in algorithm which I chose, I mean they chosen the biggest one dimension. It doesn't matter which the dimension of space. If our dimension, real dimension, will be lower, so this algorithm would work for this problem. Because if points really stay closer to each other, they will be split together by this algorithm.
You also can use a principal component analysis. Is very ancient method for such tasks. The one of the state of the art for that is TSNE, SNE, stochastical neighborhood embedding. Non-linear. It's non-linear projecting to the low-dimensional space, 2 or 3 dimensions.
But this is not too clear.
Yeah, but you can non-linear.
As I know, TSNE works only for the 3-dimensional space and big.
3 and 2.
Yes, but my dimension actually is equal to 4, and this is just one of the case. We have a more complex.
Yeah, you can use it for a large number of dimensions, but it projects onto that space you can see.
Oh, yeah, it's nice.
And you can involve your intuition to that.
But maybe now to speed up the speed of works currently in our algorithm, because our investigations now goes too slow, and our laboratory can't publish works too fast because it's important for biologists. They this is just a kind of engineering law. But
Okay, thank you. Other reporters, presenters, Artemiy, yeah, Boris, okay. copy.
Okay. So my name is Artemiy. I think my was here talk from Institute of Genetics, and my master's topic is reviewing research institutes and their interactions, a case study of me and miRNA research. So this, first of all, we'll discuss the motivation of this topic. So why we should do this. Then we will discuss any issues, affiliation with identification problem, some results, and what I'm going to do in the next semester. So, first of all, we consider author identification problem. So, for example, we have two people, so two persons. One is John Smith, another John Smith. They have the same name, they work in the same institute, in the same laboratory, but we know that they are two different persons. We know that they we know each other, or each of them, and so we can differentiate them when we see them. But if we want to differentiate between them when they publish, so on the information they provided in the article, so their name, their affiliation, so we don't have, for example, date of birth, we don't have their room number, we don't have anything, a lot of information. So, for example, we took this from PubMed database. And so in that case, we can misunderstood and think of the second John Smith of that one as of the first one and say that this is the same person. And so this is the problem of author disambiguation, how to disambiguate between authors based on their topic, on their name, on their affiliation, or maybe some other information gathered from papers. So there are some current solutions you can put here. So they perform pretty well. For example, here it's where's the mouse? Yeah, 90% of metric, 92% F1 metric. So, but that's not the topic of my work. So, why I told you about this author disambiguation problem. In the laboratory, we thought that it would be a good idea to differentiate between author disambiguation problem and affiliation disambiguation problem, because often affiliation or institution name is used in author disambiguation problem as a feature of an author. But we thought, why can't we just extract this affiliation name and try to disambiguate it in a separate way, and then in an iterative manner solve author disambiguation problem and affiliation disambiguation problem. So, for example, we clustered affiliations, we clustered author names, then we take author names and see references between affiliations and author names. So in that case, in the iterative manner, that would somehow, maybe, we don't know, but we have an idea that we need to check, somehow increase the accuracy of author and affiliation disambiguation problem. So my aim is to develop a utility that disambiguates affiliations and provides examples of its usage for English. So I'm talking right now only about this author affiliation disambiguation problem. So what's the problem? Why do we need to solve it? You can see some problems here on the presented on the slide. You can see that authors often, and it's a very often situation, they provide an email inside of an affiliation. In the paper, they provide the full address of their institution. They make mistakes like here. They skip some spaces, for example, and sometimes the name of an institution is changed. So, for example, like here, so it was Siberian division of the USSR, now it's Russia. And moreover, sometimes you see affiliations are mixed. So, if you have, for example, two co-authors of one paper, you may have Institute of Cytology and Genetics and MRC Clinical Science Center in one affiliation. So we also should somehow split them to understand which institutions working the paper. So there is a problem, but you can see we can see in this table, although there are some mistakes, there are some emails, maybe some addresses and so on, you can see that some common parts exist in both. names. For example, this Institute of Bioorganic Chemistry, like Russian Academy of Sciences, Novosibirsk. So we can try to somehow extract these common parts to like disambiguate affiliations. So what are my issues? Perform some data preprocessing. You should understand what, and I'll tell you what. Then trying some promising, of course, yeah, similarity in clustering algorithms. Then try this clustering on Novosibirsk affiliation data set and write some scores that are like applicable to clustering results. So in that sense, cluster is a subset of affiliation sets that are alike. For example, like Institute of Cytology and Genetics and Institute of Cytology and Mixed Space Genetics. So this like should be should come to one cluster. So what I do in data preprocessing right now, like these are the working algorithm. This is the working algorithm. So first of all, I remove email, zip, and other non-institutional artifacts utilizing regular expressions. Then I lowercase and leave only characters and space and the comma in an institution name. Then I split affiliation if it contains 7 institution names. Also, this is done by utilizing keywords and regular expressions. And extract only name and country from affiliation. So in that example, for example, as I saw, we have this Institute of Psychology and Genetics and MRC Clinical Science Center. It will be split into these names, like Institute of Psychology and Genetics Russia and MRC Clinical Science Center United Kingdom. So maybe in future I will try to introduce city in this name chart. For now, it's like just the institution name and country. I've tested this, so clustering. So first of all, what is a database? It is a set of 100 objects. It consists of 100 affiliations from different Novosibirsk institutions, so like cytology, sort of bioorganic chemistry, organic chemistry, and so on. We know that there were like 62 unique institution names. Then we tried 2 different similarity measures between like strings and different clustering techniques, and the best that showed like the best results was DB-scan with epsilon 0.009 with minimal samples of 5. So it means that if we have less samples in the cluster, that is considered to be a noise. So like we want to aim only on big clusters because we don't want like to see one organization that published in our topic like 20 years ago. We don't want to see. We want to see dynamics. And the metric was so-called marginal metric over 6 mer features. So K-mer, here I introduce the notion of a K-mer, as you can see on this picture. Here a K-mer is just like we take a K character length substring from a string with a shift by 1. So, for example, if you have Institute of Cytology and a K-mer, we will get INS and ST and so on. So this will be the K-mers. And so we formed a dictionary of such K-mers, of all possible K-mers from our data set. And we looked at it like, is some K-mer present in our name or not? And so using these feature vectors, we cluster them with DB-scan and get like 0.986 V-measure. V-measure is somehow the same as F1 metric, but you can think of it as F1 metric, of course not, but it's, in some sense it is. So, and this is a good result, pretty good result. In here, numbers are given for the big clusters, so not for the noise that I just talked about for the big clusters. So what are the drawbacks of current solution? Is like with the growth of features, so with the growth of data set volume, then the number of features will grow. So as I said, we use K-mers as a features. If we have more diversity in data, then we'll get more K-mers, number of K-mers, and that's why the number of features grows and computational complexity grows. And DB-scan is not an algorithm that is like, it is a polynomial will take long to like calculate polynomial kind of calculations. So the problem is that kind of cluster data sets. Well, differences. Second point, what I meant, what I wanted to make here. So I will just eliminate that. And yeah, so the current solution, unions clusters with like names, like Institute of Organic, Bioorganic, Inorganic Chemistry, they appear to be in one cluster. So that's not good. We need to somehow also think about how to work with that situation. So what is my further work is like, of course, I want to introduce the secret consideration of affiliation to maybe it will give some better results. Then I want to try another approach based on sorting and then pairwise consequence similarity measuring that will speed up the decrease the computational complexity and speed up the work of the algorithm, which is good because we want to like cluster big data sets, for example, millions or tens of millions of affiliations. And next, I want to use the tool to provide some statistics for miRNA search query from datasets for dataset from PubMed. So like distribution dynamics, their interactions, maybe some spread of knowledge, and so on. And the final step is to use this affiliation disambiguation problem solution in author name disambiguation problem in an iterative manner. We don't have the algorithm, but we'll develop it later. I hope so. So thank you. That's my current state.
Okay, thank you. Questions?
Why don't you use something like orchids or the surgery where they
this is another solution. This is not what solution we work with. So you want to be it almost unsupervised. So all the stuff like Scopus ID, like Orchid ID, they are good, and they solve the problem of identifying the author, of identifying the organization. But for example, Orchid ID is not very popular between scientists, and the Scopus ID is like you should always put your ID in your paper. That's not what authors do. They don't do it. That's the first point. The second point is that, for example, Scopus database already have some clustered names of organizations and authors. So it can identify the organization and author, but it's only inside of the Scopus environment, inside the Scopus data. So, for example, from PubMed are not present in Scopus. And a lot of authors from PubMed are not present in Scopus. And if you have, for example, another platform that want to do that kind of analysis and that kind of like having some graphs of distribution dynamics and so on, you will not be able to do that having like only Scopus IDs and so on. So that's the main idea here, just to eliminate supervised and crowdsourced data and work only with unsupervised algorithms.
Okay.
That's all. Thank you.
Thank you.